There we go. Well, welcome back. This is a good turnout for a Friday, I think, huh? In the rain. I expected hardly anybody to be here. Well, any questions you want to look at on conic sections before I go ahead? The reason I say that is primarily because we have our next test coming up on Wednesday. Oh boy, I got a brand new pen. I must have, something happened to it. So exam 3, the last midterm, is on Wednesday of next week. It covers through conic sections. Told you the sections last time. I'm trying to remember the first one now. Does at least 11.1 through 11.5. Say again? 10.8 was the other one? Okay. Is that it, right? Okay, so 10.8 and chapter 11. Problems similar to homework. There is a practice exam on Canvas that's got most of the kinds of problems you'll see, not necessarily all of them, but it'll at least give you the flavor of the exam. We'll review on Monday, and I think we'll probably just review. Possibly we'll do a little bit of new material if we don't finish everything today, all right? Today's material will not be on the exam. It's going to be out of section 8.4 on moments and center of mass, those kinds of things. All right, so I did prop up any questions. Did you try the conic sections homework is not due till after the exam, but I still have conic sections on the exam, so make sure you at least look at the homework problems and the practice problems, even though I won't require the conic sections until the Friday after the exam. Yeah. Are there any new sections for the final? Yeah, chapter 8 section 8.4 that we'll do today will be on the final, and maybe one more on differential equations depending on how things go. But that'll be it. No more than 8.4 in differential equations in addition to what we finished last time. Okay, let's get rid of this and charge ahead. Going back to 8.4 sort of as an application of these things. It has some additional material out of physical sciences that starts off like this. A little glare on there, am I not? So we're getting near the end. Yeah, this is just about done. If I have a system of masses, let's put both of these. The mass of a set of masses they should call it the total mass. M1, M2, up to Mn is just added. You say the total mass is by adding these. So we'll say M is the sum. And then the moment of mass if they're placed along the x-axis, respectively, at positions x1, x2, up to xn, is then calculated like this. Let's see. M0 is x1, m1 plus x2, m2, the position times the mass of each of these, all added together. Okay. Then we'll say the center of mass in one dimension, since they're just placed along the x-axis, is then the moment divided by the mass. Kind of x bar seems to be the notation they have in the book now, but I think maybe they developed the WebAssign at a different time. In WebAssign, they'll call it XCM, or maybe they just couldn't do an overscript. I don't know. Will be the moment of mass divided by the mass. We'll do it that way. Now, this X bar notation, anybody had probability theory before a little bit? Has some significance in probability. It's used often for the mean, the average of something, and that's exactly what this is. This is the average position of mass for this points, and I should draw a picture here somewhere along the ways. The idea is you have a long rod here, treated as massless, a lever, if you will, and you place these masses. Here's mass M1, position X1, mass M2 at position X2, treated as a point object, all the way down to mass M sub n at X sub n on the x-axis. And there's some balancing point in here, right? You could put a fulcrum here, and what it turns out is these masses have an interesting property. If you wanted to lift a mass to try and balance it, what would you have to do? For instance, you could put a mass here, M, at the end of a fulcrum like this. We'll treat it as though it's level, but I'll give it a little tilt here, just for realism. And suppose it's a very heavy mass. Maybe it's my car. I want to lift my car up, right? And so I put a fulcrum way down here, a little triangle or something, and I stand on this end, and maybe I weigh 200 pounds. That's not a mass, actually. That's a force, pounds is. But the idea is that in constant gravity, force is proportional to mass. So it's if you divide by 32 feet per second squared gravity, you get the number of slugs that I weigh. Rather than do that, let's do forces here, because that's what we're all used to. And maybe I want to lift my 2,000-pound car, right? Where do I have to place the fulcrum to lift my car? Anybody know this one? Yeah, I have to be 10 times further. What you need is that this thing here, x1 times m1 plus x2 times m2, where my mass is m2 and this is mass m1, and it's a position x1 and I'm at position x2, equals 0 to balance it. So maybe I can kind of jump a little and get it to come up off the ground. Or maybe if I hold a feather while I stand here, it'll gradually tilt up, right? But this is what you need to make them balance, is you need to find the fulcrum, put the fulcrum at the point where those are equal to 0. This says the moment of mass has to be equal to 0. And so if he correctly says that I have to be 10 times as far away, so if I'm out 10 feet this way, I have an 11-foot pole, and I put this 1 foot, then 1 times 2,000 pounds here equals, minus 1 times 2,000 pounds, plus I'm at position 10 times 200 pounds, minus 2,000 plus 2,000 is 0. I can just balance the car on the other end, which is how slight people can lift heavy objects. You just put a fulcrum in here. Archimedes did this up with pulleys. For instance, you can take a pulley and apply the same principle. If you pull on the outside wheel, right, it's as effective as if you've got a mass sitting out here. Then if you're trying to lift a weight in here, closer in, if the pulley is 10 times as wide out here as in here, then you can pull it 10 times your weight there also. Archimedes was famous for rigging systems of pulleys and so forth. They had some sort of thing they used to attack ships that came in to try and attack the place where he was, and Archimedes' inventions helped ward off the other fleet, apparently. But he was quoted as saying, "Give me a place to stand and I can move the earth," because you could put a system of these pulleys together now. Right now you attach this one to another outside of a pulley and put the weight here instead, and you can put the two pulleys, and now you can lift considerably more weight, right? Because you've got two of these things. Anyway, so systems of pulleys could lift very large weights. The trouble was you had to pull so much rope to get it to move, right? Because you had to pull the rope 10 feet out here to make this one lift 1 foot in the middle. But it had that kind of a thing. That's where these, that's just sort of an illustration of where the center of mass comes in. Because what you're trying to do is make this moment of mass equal to 0. And x bar is actually the average position of mass. And if you were doing test scores or something, right? If you had the MIs be the number of students getting that score and XI was the score, then adding all your scores would be the number of students getting score 1 times score 1 plus the number of students getting score 2 times score 2 plus all the way down. This would be the sum of the scores, right? If M is like the number of students, the score, and X is the number of students getting it. Let's see. No, I said it backwards, didn't I? M is the number of students getting it, and X is the score. Sorry about that. And now I divide that by the number of students, M1 plus M2 plus Mn. What have I computed? If I take the sum of all the scores, this many students getting this score plus this many students getting this score plus this many getting this score, all added together, adding all the scores, and I divide by the number of students, then I've got the average score that we often call X bar, or the mean, technically is what it's called, score. And so if you take the moment and divide it by M, then you get the average. And actually, X bar is where you have to place the fulcrum. You can show if you place the fulcrum there that the sum MI XI is actually equal to 0. So if we won't do that for this discussion, but if the fulcrum is placed at X bar, then doing that computation like we did with me and my car, then it's a light car, but still, then the mass is balanced. All right. And so that's the idea when you have a system of discrete masses, right? You can compute the center of mass, which is the top part here, divided by the total mass, and come up with the balancing point for the fulcrum. X bar, called the center of mass. Now what we want to do, let's do one example, and then we'll try and do this with calculus, where you have not a set of discrete masses, but you have like a lamina, a flat plate that's so thin you can pretend it's a plane region, right? And you can try balancing a plane region in 2 dimensions. All right, so let's see. Just for an example, suppose I said find the center of mass now in 2 dimensions, given, and so this will be X bar, Y bar. You find the coordinates, you can balance it in both directions. If I have this one, mass M1 is 1 pound, let's say, and mass M2 is 2 pounds, and mass 3 is 1 pound, are placed on a triangle at 0, 0, 0, 1, and 1, 0, respectively. How about that? So I've got a triangle like this. Here's Y, here's X, and I place 1, 2, and 1. This is a 2-pound object. This is a 1-pound object. Again, strictly speaking, pounds is force, but it's proportional to mass. And then M3 is 1 here. So 1, 2, and 1. What is the center of mass of that thing? Now you have to calculate for each direction. For X bar, we compute. We're now going to call the moment of mass my. Why don't we call it mx? This always bugs me. It's just tradition. I don't know why they picked my for the x balancing point, but I think it's because probably the y-axis, right? The moment about the y-axis, yeah, along the x-axis about the y-axis, is what? Well, we said that is supposed to be m1 x1 plus m2 x2 plus m3 x3. That's the moment. So we just add these. 1 times 0 plus 2 times 0 plus 1 times 1 is just 1, right? That's the moment in the y direction. And then m, the mass of these things, is just add up all the masses. m1 plus m2 plus m3, according to our formula, is 1 plus 2 plus 1 is 4. And then x bar is just, instead of m0, since we've got 2 dimensions, we'll call it my, the moment of mass, over m, is 1/4, the quotient of those two. So apparently I can balance these 3 masses, suppose they're rigidly connected with massless wire, by putting the fulcrum right here at x equals 1/4, right? Now I want to balance it in the y direction too, because maybe now I'm actually taking a massless piece of plastic here, and I'm going to turn it aside, and I want to find a balancing point so I can balance the triangle on my finger. So it has to balance in both the x and y direction. So where should the fulcrum go along the y-axis? We can calculate that, right? Also, mx, the balancing point along the y-axis, is m1 y1 plus m2 y2 plus m3 y3 is 1 times the initial y coordinate was 0 plus 2 times the other y coordinate is 1 plus 1 times 0. So each mass times its corresponding y coordinate is equal to 2. So there's the moment of mass along the y-axis. We use the same masses from here. We already know it's 4. So y bar is equal to mx over 4 is 2/4. It balances at the point 1/2 here. Well, that makes sense because it's kind of like you can imagine these two masses sitting on each other on top of the y-axis, weighing 2 pounds, and then there's 2 pounds over here. You balance it right in the middle, right? So this is at 1/2. 2 pounds here and 2 pounds here, gravity pointing that way, makes it balance right in the middle. So now we say the center of mass is just the coordinate pair. The place you could balance if you took the triangle and turned it on its side. Would be at x equals 1/4, y equals 1/2. All right. So that's for a set of discrete masses, and it's more motivation than anything. I did give you a little problem right at the beginning of the homework section just to do that, to see the discrete analogy, because once you do that, then the calculus becomes much easier. These things are all sort of, I wish I could remember the quote from John von Neumann. He was one of the famous physicists well, he was a combined physicist, mathematician, and computer scientist of the 20th century. He had such a great statement about how important calculus was, and can't quite remember it. It's a long statement, but uh, a lot of calculus is developed by looking at these analogies to the discrete case as the masses get smaller and smaller. For a continuous object, instead of we now use its density function. And section 8.4 really doesn't do the one-dimensional case, so I'm a little reluctant to write it down, but maybe I should just write it down for comparison. Let's call it rho of x in one dimension. And so this is like grams per centimeter or slugs per foot, something like that is its density. And what you get, instead of summing the masses to get the mass, you integrate the density function to get the mass. For a one-dimensional object, say you have a rod, they say like a one-dimensional object with mass they might call a wire, so thin you can treat it as one-dimensional. So here's I think the book calls it a wire. Here's a wire from A to B that has a continuously changing density function. Instead of adding the masses, you're taking the limit of the sum of these little masses. You can think of breaking this up into little pieces, right? And you can say, well, approximately the mass is the sum, k equals 1 to n, making little masses m1, m2 to mn, and the approximate mass of each of these little pieces is the density function at any point in that interval, say xk star, times delta xk, right? We could say this is the approximate sum of all these little masses. You take, for an object of uniform density, you'd say, well, the mass is just the length times the density, right? It gives you its mass for a one-dimensional object. And so we treat these individual ones as you can just take length times density. That's what this is. So the length of the pieces are delta x1 down to delta xn. And so this is mass density times the length of the kth piece. And for something of uniform density, you'd say that's the mass, right? Mass k. Density k, length k. Now, if this density function is continuous, then as these get smaller and smaller, each of these little increments, each of these little things gets a closer and closer approximation, actually, to the little piece. And if you took the limit of this, as the number of pieces goes to infinity, you'd get the same number no matter how you partition this up, as long as rho is continuous. And that must be what we want to call the mass. This is just the limit of this approximation by breaking up into little pieces and taking as though it's constant density times length to get the mass of the kth piece. So this is the mass for a one-dimensional object. And we can do a similar thing. Then the moment of mass is just the position x. I mean, if you do a similar calculation, m0 is approximately the sum xk times rho of xk star, rho of xk star, delta xk, because right at the moment was the position times the mass. So this is the kth position times the case mass. That gives you the moment. And so this approximates the moment of mass. I should move this before I kill myself, shouldn't I? I'll bring some comic relief to class here. All right, so that would be the moment by breaking it in a lot of pieces. Now you take the quotient. Now you compute this one, and the limit as number of pieces goes to infinity. You get x rho of x dx is the moment, integrating along the little wire here from A to B. And then you can define x bar to be the center of mass. xcm or x bar is then m0 over m. Just like before, it's just you compute it with integrals instead of sums. So that's the power of calculus, is to do things like that. And like I say, John von Neumann's quote would really bring this out, how calculus has really transformed our ability to do these kind of things. Then we can extend that to more dimensions, right? This one will not be on the homework. That's the one-dimensional case. I just wanted you to see how it extends. Next, consider a two-dimensional object. A lamina, something we'll treat as a plane region. And suppose it's of this kind of shape. It goes from a function. I don't like the way the book did this, but I'll just use the same letters. I like to call F2 the function on top. They call F1. That's the only complaint. It's just a matter of notation. But I like to put F2 on top, just what I'm used to. All right, and suppose this lamina extends from A to B. They call this a vertically simple region. It's got straight lines on the side, or maybe these meet at a point. And this is your plane region R. How can I find the mass of that lamina if it's uniform density? You can do this with non-uniform, but they didn't, so I won't. Suppose it's of uniform density, rho. What's the mass? Well, I should be able to take the density and integrate. Now this density is actually like in grams per square centimeter, or kilograms per square meter, or slugs per square foot, something like that. So it's per square unit instead of per unit length, since it's a plate. E.g., kilograms per square meter. E.g. means for example. And then I can compute this. The mass is what? If it's uniform density, then I just take the density function times the area, right? We said. In Calculus 4, you'd learn how to compute this as an integral, so I won't go ahead and do it, but you can, if it's varying density, you can do it as a integral of an integral, and you do that in Calculus 3, excuse me, if you're going to take that. So I'll leave that out, and we'll just do uniform density here like the book does. And so what is that? That's just the area function is the integral, if this goes from A to B, integral from A to B, of rho times F1 minus F2. Right, so there's the mass. And then what ought the moment of mass be? We'll call it my again. It similarly ought to be this just with x put in there, like we did in the last one, right? Because we're taking position times mass, right? This is the little infinitesimal mass, they say, integrated along the thing. And so if we just put integral from A to B of x times rho times F1 minus F2 dx, that'll be the moment. And then finally, if you can see through the thing here, I'm just going to write the same thing I did before. X bar is my over m, just like the discrete case. Stand up if you have to for a second. I don't want to write it at the top. I'll go back up to the top now. So you can compute that for the balancing point, X bar for the lamina, because now it's density, right? You're thinking of breaking it up into little intervals of width delta xk, right? You make a bunch of little rectangles here. This is what this is doing. Each of width delta xk and height f1 of xk star minus f2 of xk star at some intermediate point in here, xk star. And so it's the approximate mass is the sum k equals 1 to n of the mass of the kth piece, approximate mass of the kth piece, which is the density times the height, f1 minus f2, times the width, the xk. Kind of squeeze that a little bit. But height times width gives you the area of the case rectangle times the density. And now you can see how to do this with non-uniform density. If it just varies with x, you could put rho of xk star in here and do a varying density. They just did constant density in here, though. And so this is minus in here. It's kind of hard to see. If you take the limit of this, you get this formula, right? This is the height times width times the density of the kth rectangle. Add them all together as approximation. Take the limit by definition of the definite integral. It's this definite integral is the limit of this here. So that's where those formulas come from. And this is what you want to know for the section mostly, is those formulas, all right? Now we can compute balancing point for something for real. Hold on a second. Don't want to keep you guys late on a Friday, right? All right. Here's an example out of the homework. Suppose I say, find the moment of mass and balancing point, x bar, moment, my, and center, x coordinate of center of mass. For the following plate. It goes between y equals x squared and y equals 9x. And if, suppose that the density function is 2 grams per square centimeter. All right. What is it? You should read that story about Archimedes, by the way. It's kind of fun. You just go Google Wikipedia Archimedes. It's probably on there. Anyway, so where's the point? I could put a fulcrum here, and if I just, put in a little groove here, it would balance the thing. X bar, XCM. I just have to compute those formulas. I'll say the moment of mass along the x-axis, my, the moment about the y-axis, if you will, is the integral of x times f1 of x minus f2 of x dx from a to b. That was what we said came from the continuous analogy to the discrete case we just did, right? So what's that? It's, well, this thing goes from where to where. We have to find the intersection points, right? Where do they intersect? Just set those equal, right? X squared equals 9x. And you can solve that easily, right? It's x squared minus 9x equals 0. Factors is x times x minus 9 equals 0. Evidently, x equals 0 or x equals 9. So that's where it intersects at 0 and 9. And I need to integrate from 0 and 9. Let's see, f1 has to be the top function we said, so that's 9x. And f2 has to be the bottom function, that's x squared. That'll give me the moment of mass. So let's see, it's 9 halves x squared minus x cubed over 3. Plug in 0 and 9. Now I've got 9 cubed over 2 minus 9 cubed over 3 is 9 cubed over 6, which is 81 times 3 over 2, 243 over 2. I think it comes out to be, yeah, 243 over 2. So there's the moment of mass along the x-axis. Then I need the mass. Should have computed this one first, really. Is just the integral of the density, right? Along this space. So it's rho times f1 of x minus f2 of x dx. It's the same integral just without the x in it. So it's integral from 0 to 9, 9x minus x squared dx. I like to do this one first normally. I don't know why I did this one first. I guess because it's on top of the quotient. But do this one first, and then all you have to do is put x in to compute the moment, right? So it's the same integral except for the x in it. All right, let's see. So this is 9x squared over 2 minus x cubed over 3, evaluated at 0 and 9. Let's see. Oh, I'm sorry, that's what I just did. I forgot the x in the last example, didn't I? Did it? Oh, nobody caught me. I dropped my x out on the last one. This one comes out to be 243 over 2. Right? And the last one, that's mass. And my should have had this extra x in here. X times 9x minus x squared. I dropped it in this step, trying to go too fast again. So now I get, let's redo this one. Sorry about that. Integral of 9x squared is 9x cubed over 3. And then I've got integral minus x cubed gives us minus x to the 4th over 4. Plug in 0 and 9. That comes out to be I think 3. I think it's 3,402 over 5. That's what I wrote down. Hope that's the right one. We can compute it. Let's see. That's 9 to the 4th is the trouble. Over 3. Well, let's leave that out. I know what the quotient is. And then you compute, just in case. Then we'll say x bar is the my that we just computed divided by m. Comes out to be 27/14. So what was this? Anyway, so we'll say you divide this one by this one and get x bar. That's the idea. So there's the center of mass in the x direction. You can also do the center of mass in the y direction. Integrate over the solid. Now I want to make an additional note on this. When rho equals a constant, such as we just did, something interesting happens. X bar becomes the integral of x rho f1 of x minus f2 of x dx, a to b, over the integral without the x in there, rho f1 of x minus f2 of x dx, right? That's what we just found. This one was my and this one was m. But if rho is a constant, it can come out of the integral, right? You take it out of the integral out here, and you take it out of the integral right here, and they can cancel, right? Because now it's just rho over rho cancels. And what you get here is still usually written as my on the top, but we'll just get integral x, f1 of x minus f2 of x dx on top from a to b. And we'll still call that, let's call that my still. But on the bottom, what is it? Oops. It's integral from a to b of the top function minus the bottom function. What is this geometrically? If I just integrate f1 minus f2 over the length of the interval. Remember from last semester? Yeah, there you go. It's the area, right? Right, because what I'm doing is I'm adding up these rectangle heights, and just without multiplying by row, it's just adding up the rectangle areas, I should say. Adds up the rectangle areas, takes the limit, it gives you the area, A. So really, in the special case of rho being a constant, which is all they do in this section, just to keep it simple till they do the harder stuff next semester, you're just taking my over A. And on simple objects like a disk, you can find the area of it just by formula, right? Pi r squared. And you don't have to do this computation. That's kind of neat, right? And what's more, this number, without the rho in there, is also called the centroid. It's the center of mass for an object of uniform density, or it's the centroid of the geometrical region, a purely mathematical thing. Centroid x coordinate, if you like. And there's a y coordinate too. And you can do some neat things with it, it turns out. There's a theorem going all the way back to the ancient Greek named Pappus. That says if you take a plane region of area A, which you have to compute for this anyway, revolved, he didn't use the words x-axis because they didn't have coordinates back then, but revolved about the x-axis, that doesn't intersect the region. No, I'm sorry, revolved around the y-axis. I wrote the wrong one. Y-axis, not intersecting the A. Has the volume V equals the area of the region times 2 pi x bar. In other words, it's the area times the distance traveled by the centroid. The idea is this: you have a region here, A. Maybe I'm going to make a donut, a torus here, right? I revolve this around the y-axis, so the disk revolves all the way around. How much volume does this donut have if it's, say, 2 units from the y-axis and it has radius 1? All we have to do is say the area of the unit circle is pi, right? Have to do this quickly. Pi r squared, but r is 1. And then the distance the centroid travels. You can use symmetry in these problems. When you've got something that's symmetric like that, the balancing point of uniform density is obviously right in the middle. X bar equals this position 2 if it's 2 units out. So the centroid is at 2. The area is pi. We say the area is the area of the circle, pi, times the distance the centroid travels is 2 pi r. 2 pi times the radius is 2. And so we got 4 pi squared is the volume of the donut. You can just take the area of the circle times the distance the centroid travels, and you can do that more generally. It doesn't have to travel in a circle, it turns out, as long as it doesn't turn so sharply that it intersects its plane region as you turn. You can do this on more general curves too. Well, that's it for today then. Time to go enjoy a weekend. Kind of interesting stuff, I think, huh?